So welcome to Statistics Former Student Network talks. Today, we are happy to have Robert Reynolds, data scientist at NASA Human Health and Performance Director at Johnson Space Center in Houston. Let me introduce this speaker. Robert Reynolds earned his Master of Public Health in Epidemiology from the University of Arizona in 2001. His PhD in epidemiology from UT Health in 2013, and his MS in statistics from Texas A&M University in 2017. He is professionally accredited statistician by the American Statistical Association and self-taught data scientist. But as statistician, this is automatically data scientist. Over the course of his career, Dr. Reynolds has worked in research units in several universities, led teams of epidemiologists and data scientists in the health insurance industry, and for the last decade has offered expert opinions in state and federal courts on epidemiological and biostatistical issues. In the context of occupational epidemiology, his research has focused on the long-term health of workers in unique occupations, such as professional athletes and astronauts. Since 2019, Dr. Reynolds has served as data scientist for NASA, Human Health and Performance Directorate at Johnson Space Center, where he works as part of a multidisciplinary team redesigning the process by which NASA conceptualizes and manages human system risks of spacecraft. Robert's talk is titled Only What You Take With You, Research Methods for Human Systems Risk in Space Flight. Robert, audience is yours.
Thank you very much. So what I'd like to do today is, if I can get this to work here. There we go. Start with a couple of disclaimers. First is that I'm just here as an alumnus of Texas A&M and not as any sort of official representative of either NASA or KBR Incorporated, who's the contracting company through which I'm employed. So any opinions or ideas that I express here today are pretty much my own, and you shouldn't try to pin them on the agency or the company or anything like that. And wherever possible, I've given you links, but everything that we're going to talk about here in this talk today is publicly available. It's all in the public domain, so there's no secrets. I'm not going to be going to jail for sharing anything I shouldn't share. Like that. And really, what I'd like to do today, I've seen some of the talks in this former student network program where it's introducing interesting new statistical techniques or things mathematical that haven't been tried before. My talk's going to be a little different today. Instead of that, there's not going to be any theory or derivation or anything like that, but rather it's going to be looking at the unique research environment that spaceflight health poses, and then thinking about different ways to use the tools we already have to try to learn from what little bit of data that we actually have from spaceflight experience. So in that vein, we're going to first talk about spaceflight health research as a research domain, what those challenges are that make it so interesting. Then I'm going to shift gears a little bit and take you on a little history lesson about directed acyclic graphs and causal diagrams and all the related concepts there, because I'm going to show you how we're then using those things at NASA today. And then I'll end with just some other kind of off-the-wall examples of things I've done in creative thinking about how to squeeze more information out of the existing data. So let's begin here with the research domain idea. What we've seen with spaceflight health research is an evolution, and it's a very natural one. In the earliest programs, such as Project Mercury, we had 6 flights with 1 person on them each, most of them very short duration. The first couple were only about 15 minutes suborbital. Then the orbital flights got progressively longer till the last mission there was 34 hours. These flights were very exploratory, both in a technology sense and in a medical sense. Many people thought astronauts wouldn't be able to function in a microgravity environment. There were wild predictions about being unable to swallow, about people's eyes rolling back in their head and being unable to use their eyeballs. So a lot of it was just, let's figure out if our machines work and what happens to people when they go into zero G. And that was really written into the program objectives for Mercury. That was, of course, the space race, as it's become known. And the primary objective of the 1960s then was to get to the moon. So after Mercury came Gemini, and there was, similar to Mercury, more kind of observational, just what happens, can people see the ground from space, all these different medical research light kind of topics. And then it was all about getting to the moon. Once that cleared out, we had our first space station, our first US space station, and that was Skylab. And so at that point, it was actually dedicated to biomedical research. This is where people were proposing protocols, getting them approved, and having the astronauts execute them in orbit. And these days were up to 88 days at longest, I believe it was, in 3 different flights. So we gained a lot of information there about cardiovascular function, physiological change, beyond just what happens when you immediately get into zero G. So this was after a month or 2 or 3 of exposure. What does the human body look like? Now we're at the ISS, where we keep extending the continuous stays out past a year. It seems like every time you look at the news, there's somebody who's just broken a record for how long they've been in space. And we've got a more mature understanding of what the changes look like up to that point, of about a year or so. And we've developed some countermeasures. And here you can see one of the astronauts on the treadmill that the ISS has. Essentially, there's a harness there to sort of rubber band you to the treadmill belt so that you get some shock of simulated gravity against the belt itself there. And that's designed to maintain aerobic fitness and try to maintain some bone density in the load-bearing bones. So as we look forward from this point out to lunar outposts, the lunar gateway stations, surface stays, and eventually, hopefully, going to Mars, we now have a new set of challenges that we have to go after, which is what happens when we're out of the Earth's protective magnetosphere, when we spend a lot more time in zero G. If we spend 3 to 6 months on the float trying to get to Mars, will people even be able to function once they get there? They have to re-enter a gravity environment, try to walk, all these things. So how is this actually going on at NASA? Well, there's a couple of different organizations here that are doing the research. The first is the Lifetime Surveillance of Astronaut Health. And this is exactly what it sounds like. It started out as the longitudinal study of astronaut health back in the early 80s, and it's evolved into this view of kind of just watching everybody across the lifespan to see the after effects of spaceflight, see how they age, and look for differences. So this is at Johnson Space Center, and this is the main epidemiological unit of the research going on at NASA. Then there's the Human System Risk Board. We'll hear more about that in a little bit here. Human System Risk Board tries to bring together all the evidence from the flight surgeons who actually deal with the astronauts pre-flight and in-flight, the epidemiologists who are doing research, the biomedical research labs that have the subject matter experts. And this board then tries to synthesize all the evidence and opine on the overall risk picture that NASA has at any given moment. Where the money comes from for this is a couple of different places. Here at Johnson, there is the Human Research Program, which we see on the left there. They're the main matrix funding organization that essentially is a grant-giving organization. They fund the biomedical research labs within NASA, and they give grants to external investigators as well, often in very targeted ways to try to develop the evidence that the agency needs to mitigate these risks. Then there's an offshoot of that at the Baylor College of Medicine here in the Med Center in Houston that HRP funds, but it's TRISH, the Translational Research Institute for Space Health. Their mandate is to try high-risk, high-reward type off-the-wall stuff. So if you want sort of the progressive science that is going to solve the big questions, you do that through HRP. And if you want to try to develop some innovative technology or try something zany, you go to TRISH and see if you can get them to fund that. Okay, so that's kind of what's going on as far as what we're trying to do and how there's bureaucratic structure in place, but what makes all of this challenging is a natural question. And what it really comes down to is the data and the methodology that we have to use. So worldwide, all in, Soviets and the United States program, there's only been about 600 people that have crossed the Van Karman line and been what we've considered to be to space. On the US side, we've had 22 astronaut selection classes, starting with Mercury 7 in 1959 and going through the most recent class selected a couple of years ago. And that has trained 348 individuals. There's actually 350 selected, 2 dropped out along the way, one in the 60s and one a few years back. As of mid-October of this year, that means there's just over 11,000 person years of observation time. So if you're used to the health sciences and looking at any sort of incidence rates and long-term mortality and things of this nature, that's not a lot of information. Compounded on that is the lack of diversity. So the median age of a person year is about 51. And as you can see from that distribution, people get picked in their early to mid 30s, and then they fly till they're probably in their about mid 50s, and then they start to drop off from there. And just by the nature of how many people have been picked and when, we really just don't have a lot of people that are over age, say, 60, 70. So we're still learning about what does healthy or unhealthy aging look like in this astronaut population. On top of that, it's 85% male and 90% white historically. That's obviously changing now as they seek to pick more women and minorities, but it's a slow process. They only pick a dozen or so astronauts at most in a class, and not very often. This is, of course, problematic because many of the medical conditions that we care about related to spaceflight have low incidence rates. So you're not really going to see any cases if you don't have much flight experience or much lived experience from people who do. And then just for fun, we'll throw on top the healthy worker effect, which, if you're unfamiliar with that, is both a selection bias and a survival bias effect, whereby only the healthiest sort of people get picked for a job and then can remain in the profession. So it's unclear exactly what effect that has here. One thing we do know is that the astronauts have much lower mortality rates and incidence rates of most diseases than does the general population. Another issue is complexity. We've got 29 identified risks, that the agency actively manages in one human health concern, as they call it. And that's just another potential risk that hasn't yet been elevated to that same level. And so that's what the HSRB, the Human System Risk Board, does, is bookkeep all those risks and try to marshal the evidence and communicate a risk posture out to the rest of the agency concerning those basically 30 risks. Within those 30 risks, there's at least 452 identified factors that play a role in causing the problems we care about. We identify 5 hazards of the spaceflight environment. And those are ubiquitous exposures that happen every time you go to space, and 7 mission-level outcomes. And those are those things that the agency wants to prevent. In between that chain of events from those hazards to outcomes, we see 440 intermediate factors along the way. That leads to 1,671 hypothesized connections between all of those factors. Naturally, that sort of complexity leads to an organization where we're looking at the risks in silos, because that complexity makes it difficult to understand how everybody ought to play together. Okay, so let's take our detour through the history of causal diagrams. Now, if you've never seen causal diagrams before, it really started about 100 years ago with a gentleman named Sewell Wright. He was looking at the genetics of guinea pigs, and he actually invented this method, or at least maybe perhaps the math behind it, to figure out the inheritance patterns between when you would breed particular parents of a guinea pig and get something rare. So there was some sort of code pattern, if I recall correctly, that people were having trouble understanding how it was being passed down. So even in the days before Watson and Crick, he invents this path analysis idea where you decompose a correlation matrix between variables, and then you can get these path coefficients, which are, how do we describe those, partially, trying to remember the exact language, but essentially they're standardized regression coefficients. There's a particular term and it's escaping me, but what you can do then is multiply it over the paths, and that will give you back correlations. It's handy because you can also do it with latent variables, so you don't necessarily have to measure everything in the system if you have the right combination of measurements. So that brings us into structural equation modelings. Standardized partial regression coefficients, that's what I was looking for. Psychologists saw this method and decided it was useful, and they expanded into something more sophisticated in the 1970s. In this sort of conception, we have what you see here as the structural model and then a measurement model. So this is getting very formal and technical about how we relate measured variables, like variables 1 through 6 here, into latent variables or things that we can't measure directly. So that structure model talks about how the latents maybe work together or how they cause each other. And the measurement model is how you use the measured things to define those latent variables. And this allowed them to estimate residual variances and covariances between things that weren't causally related, and a very handy technique. By the 1980s, Judea Pearl at UCLA starts playing around with the idea of causal networks, and he invents what's called Bayesian networks. So here he recognizes directed acyclic graphs as a construct. Then he says, what if we could put a joint probability distribution in this thing so that the probability of an event happening is dependent on its parents' inputs? And so that's what you see here, where the probability of getting a good career is dependent on having a good job and special funding. And the probability of getting a good job or special funding is dependent on economic environment and so forth. So you can use that to either calculate downward across a chain of known events or to work backwards. So if you have a promising career, or you think you do, you can look back and say, all right, what was the probability that there was a favorable economic environment when you started, or that you received special funding, or what have you? Kind of a ridiculous example there, but the point is that this allows you to reason in both directions, and it's quite powerful from a probabilistic reasoning perspective. By the 2000s, epidemiology and economics discovered directed acyclic graphs. So here the concern is, if you're fitting a regression model, say for the effect of A on D in this example, which variables along the way that you may have also collected should you put into your regression model? Should you adjust for B? Should you adjust for C? Should you adjust for E? Well, looking here, this on the right-hand side, all this output is from daggity.net. I forgot to put a link there. I apologize, but it's a nice web-based tool that allows you to sketch out your own causal diagrams. And then it does this analysis part for you here on the right. So it's telling us, Z is an instrumental variable if you care about that. Pink arrows from C down to A and D are telling us that that's a classical confounder because it's a factor that's related to both exposure and outcome. B has those green arrows, which means it's on a causal path, and so forth. If we were to mark E as something we wanted to adjust for, it would then turn the arrows connecting to it into pink because you'd actually be creating bias. You'd be adjusting for a collider. So it'd be collider bias as it's known. Economics is really the ones that came up with the instrumental variable idea, and that is figure out how Z predicts A and then use an imputed value of A instead of the actual value of A, and that could remove some unmeasured confounding. So these things end up being very useful in causal inference analysis, and there's a lot of development work still going on in economics and epidemiology today related to all that. Then stepping backwards in the chain a little bit, there's social network analysis. And I put this in last because it's not really related to DAGs particularly, or causal diagrams particularly, but rather just any sort of network. It mines the structure of that network and tells you what's important. So this came out of social networks, and some of that seminal work was done in the 1930s, where they would look at schools and ask children, who are your friends? And so you get these bipartite connections about the kids identifying each other as their friend groups, and you could get some kind of network that looks maybe like this. This one is actually my LinkedIn network connections from about 10 years ago. And you can infuse these things with a lot of information. You can see the different communities that it detected are colored differently. And if you were to look at who those people were, those were associates of mine at various jobs. And so they are very close to each other and not to the others because, changing companies, you don't necessarily have people knowing each other across companies, but within they certainly do. And the idea here really is that of centrality. So this is what's known as an ego network, but if you could see the entirety of the LinkedIn network, all the tens of thousands of users, you could figure out who the real movers and shakers are by using what are called centrality measures. Okay, so how does all of this help NASA, you might be wondering? These three publications here we put out from the agency. The first is a revision of the Human System Risk Management Plan, and the other two are technical papers, or a technical manual and a technical paper about how we use directed acyclic graphs to model causation for all those 30 risks I mentioned earlier. So this is coming off of the HSRB website, and it's highlighting the idea of directed acyclic graphs as a communication tool because it allows you to very easily represent in a visual format how you think the risks are happening. Remember, I mentioned that there were 5 spaceflight hazards and 7 outcomes that the agency cares about. So this is a visual depiction then of how you get from those hazards to those outcomes. And it allows you to build in some more information, because it could be that you know that really well or that it's suspected. So by representing with different arrows and colors and things, you can build in information about your certainty. So this is the general pattern of how the HSRB DAGs work. We start with the set of hazards there on the left, which generally, through medical issues and human degradation, if you will, lead to health and performance risks. That will in turn reduce the readiness of any individual astronaut to perform their job. That can feed up to diminishing the team's capability as a whole, a group of astronauts, and the crew capability, or I guess team functionality in this case is how well people work together, actually. And that goes to crew capability, which is the team's ability to get jobs done. And then out to task performance and loss of mission objectives. And you can see those two are marked with those vertical lines, and that's Daggitty's version of marking outcomes, because those are 2 of those 7 things that the agency really cares about. We see also coming from the bottom, human system integration architecture. So that's recognition of the fact that how well we develop our machines and how much capability we build in to do different things affects how healthy our astronauts are going to be in flight. So here's an example from one of those 30, and this is one of the simpler ones. This is for non-ionizing radiation. So you can think of this as sunlight and lasers, essentially. And so right there in that box in the middle marked environmental injury, that's what we have is skin injury and eye injury coming from the sunlight and the lasers. And that feeds directly into that chain of individual readiness to crew capability to task performance, loss of mission objectives. And if you lose enough objectives, you lose the whole mission. And so then there's a call out here about what those eye and skin injuries are. Understand then that, as I said, this is one of the simpler ones, but there's 29 pictures like this. And where possible, when these pictures refer to the same factors, we had them use the same language. So we can actually combine these 29 pictures to make one really large network. And that answers some of the problems NASA was having of understanding what is the relationship between these risk systems? How do they feed each other? And potentially, how can we avoid unintended consequences of trying to mitigate one or find countermeasures that affect multiple risks in a positive way? So this is the narrative that goes along with the DAG, and it essentially tells the story I just told you, that the central risk is eye injuries and skin injuries from sunlight and lasers, and then it causes problems and so on and so forth. Okay, so I mentioned something about the certainty of the causal relationships before, and that's where we get into this part of the scheme, which is level of evidence. So when we think about these DAGs, each arrow is a posited causal relationship. A causing B would be A with an arrow pointing towards B. And so we can think of these all as testable hypotheses. And if we want to specify how sure we are that that is a correct causal hypothesis, we can do it using this level of evidence system. And if you're familiar with Sir Austin Bradford Hill's causal guidelines from an address he gave to, I think it was the British Royal Statistical Society in 1965, he outlined 9 of these things that he thought were important aspects of a truly causal relationship. We've taken what we think are the 6 most essential and then built them so that as you progressively satisfy them, you rise from a speculative up to a strong level of evidence. So speculative being the temporality is correct, the exposure that you think is causing whatever effect is actually coming before it. So that's key, and that's the only one that's required in every case. And then analogy, you have some similar situation, or you've seen animal evidence or something that makes you believe that this is a reasonable and plausible thing that might be happening. As you move up, you're adding mechanism, which is on the cellular or molecular level, some kind of understanding of how it would actually work. You're reproducing it and you're finding it in people. So specificity is that person, place, and time aspect of epidemiology. And then eventually, when you've assembled enough evidence, hopefully it's all coherent so that in vivo matches in vitro, matches in people, and so on. That was a little premature, but there we go. The point of all this is to get to this risk matrix. And this is how the HSRB communicates risk to the agency. So we can see that there's likelihood rating and there's consequence rating. And so you can, hopefully, as statisticians, immediately recognize this as an expected value proposition. And so the consequence can be defined qualitatively as far as what does it do to us medically, what is the decrement in performance we might experience, but it's that likelihood piece that I wanted to address by trying to build out all these networks and hopefully turn them into a Bayesian network eventually. So now when we look at the overview of analytic strategies we could bring against all these HSRB networks, we can use basically everything that we saw in our little historical tour. We can mine the network structure to find dependencies, just like those, the daggedy coloring of the arrows, the green arrows, the pink arrows, find the confounders, find the things on the causal pathway, and then find the things that, because of that structure, necessarily must be either correlated or conditionally independent. And that's a way to help us validate if we got the right picture. Network analysis can help us pick the places in the network where we might want to try to insert countermeasures. Again, because it either is some kind of nexus of where the risks stem from, or because it has a good downward effect. It affects many things past it, and that will reduce risk across the board. Recognizing that just because you have one node that maybe is the highest probability, it doesn't mean it's the best target. So that's another way to select. The path analysis in SEM is another way to do regression better, particularly when you haven't measured every variable in the system. You might be able to get some estimates and understand how much of an effect something in the middle is having, even when you don't have data directly on it. And then, of course, the Bayesian network, and that's to get those probabilistic calculations that can inform the L and the L by C that we just saw. Okay, so that's the causal diagramming at NASA. Now I'm going to shift gears on you again and just go into some of these examples of other research I've done trying to use the existing tools in a different way. So the first topic is radiation and cancer in the astronauts. This is a big concern. It's not clear entirely yet what's going to happen to people when they go to Mars. There's some people who say, it's going to be deadly, we can't do it. Other people say, nah, the standard's wrong, we need to just think about it differently. But the gold standard in any research related to this would be to obtain individual dosimetry data from the people who've been to space, and then do cause-specific mortality analyses in an appropriate way. But that's hard to get, those data. And for my dissertation at UT Health here in the Med Center, I wanted to look at this question in a slightly different way. So my idea was, could I reliably estimate radiation doses based on the vehicle someone was in and how long they were in space and what their orbit was, and then use that to estimate their dose and then look at mortality? So we conceptualized this in three pieces. The first was a systematic literature review to say, are there measurements out there of dosimetry in these various orbital locations and vehicles? Then meta-analyze any that might exist and develop a tool that can do the estimation, and then actually in part 3 do the mortality analysis. And so what I really want to showcase here is just that meta-analysis part. So it turns out that the literature was ripe with measurements of radiation from all the different programs and from EVA and different orbits. What matters here, and it may be a little small to see, but is your orbital inclination. So this is how far off of the equator on an angle you're going when you're circling the Earth. Your orbital apogee altitudes, that's the maximum distance away from the surface you get on any pass around. And then which spacecraft you're in, because the different construction of the different vehicles confers different benefits of shielding. So you can see in this table on the left how many measurements went into it, and then how many hours worth of observation as a data density type measure. And then I just did a arithmetic, geometric, and bootstrap mean for each of these locations. So this we called a location exposure matrix, or a LEM. If you're familiar with lunar modules, that was the other use of LEM, so we kind of found that fun. But the idea comes from occupational epidemiology, where you would have a job exposure matrix, or a GEM. And this is a way to estimate historical exposures for someone, say, who works in a factory and they've worked there 30 years, but you just started studying them last week. So if you know what their work history was, you use one of these matrices to say, okay, this person spent 2 years doing this job, which means they're exposed to these things, and you just add it up. The other approach was to use all of those observations and put it into a mixed model in a typical meta-analytic type fashion. And that way we could interpolate and extrapolate past just where the measurements were taken. It turns out doing that worked decently well, and there was no effect of being in the upper half of the radiation distribution on either heart disease, cancer, or both combined. But I didn't stop thinking about this problem because I'm a little obsessive like that. And so thinking again about CVD and cancer and this idea that space radiation may increase the mortality rates from these things post-flight, we can set up a very simple DAG like this, where we recognize, okay, space radiation, we're saying, could be a common cause here, where it's causing DNA damage that might lead to cancer, and it's causing endothelial lining damage in arteries that may lead to cardiovascular disease. And there's the little output from Daggety that's telling you these two things would be independent if you controlled for space radiation. And that, of course, is a backhanded way of saying they're related because of the common cause of space radiation, if you believe that. So the question becomes, given again that I didn't have the actual dosimetric data, and as an aside note, even if you did, an early paper in 1991 pointed out that most of the astronauts, at least through the late 70s, had received more radiation from medical scans than they had from space. So again, small data. But either way, if you don't have the space radiation data, can you use this logical dependency to your advantage? And it turns out I think you can through what's called the modus tollens. This is an alternative hypothesis formation that comes out of logic, and it looks like this: if P, then Q, right? So if P event, then Q will follow necessarily. If you observe not Q, you can therefore say not P. A very simple example would be if your dog detects an intruder trying to break into your house, he's going to bark. If he's not barking, then there's probably no intruder trying to break into your house. If we translate that then into this CVD cancer space radiation context, we would say that if they have this common cause, their survival curves will not be independent. If you look and you see that those curves are independent, you can infer that they do not have a common cause. And that may be because it's only causing one of them, or because it hasn't caused either, or both. So our approach to this, we got information on the astronauts and Soviet and Russian cosmonauts. And we realized that there are specific methods for survival curves that are for competing risks. And the whole reason those methods were developed was for this problem. If there's information about one cause of death built into the other, in other words, if they're not independent, you'll get biased survival curves. So we thought, okay, if we do the naive approach, which is a standard Kaplan-Meier, and then do the cause-specific approach, adjusting for CVD when doing cancer and cancer when doing CVD, if there's interference there, we should see a wide gap. We should see the bias, and that would be the evidence that our modus tollens isn't working. As you can see from these 4 plots here, rows are the data sources and columns are the outcomes. They all pretty much overlap, which led us to believe that either radiation isn't causing both of these things because no one's got enough radiation yet, or that's just not a thing. It's hard to know. But at this point, what we can conclude is that it's not being detrimental to these space travelers. Okay, how am I doing on time? Good. Dehydration in Mercury space flights. So it turns out a lot of our information that we have on what happens when you go to orbit, some of it was gathered in those early space programs, as I mentioned earlier, and then a lot of it comes from the shuttle and the ISS. However, the astronauts are typically so busy when they first get to orbit that they don't do a lot of biomedical experimentation in the first few days, sometimes not even in the first week. So there's a bit of a hole in our knowledge as to how fast some of the known changes actually happen. So looking at the Mercury data set, it was obvious that there was some level of dehydration happening to these astronauts. And this little paper that you see here on the right is something that was put out by a group of NASA and former NASA folks back in, I think it was 2017 or 18. And in it were tables that actually had the Mercury data. So it was only 6 astronauts, 6 flights. So it had their pre-flight, post-flight measurements of their blood composition, their body mass, heart rate, temperature, things of this nature. So it was a simple matter to harvest it and see if we could do anything with it. So the reason you might see or expect to see dehydration in this group of astronauts, even though they were extremely short flights, is the early spacesuits. These were really what we call pressure suits. You can see it fully assembled on John Glenn there on the left, but you can see him putting it on the right. So there was this inner garment that was kind of the cotton comfort layer with a little bit of cooling, and it was air cooled, so it actually connected to the life support system of the Mercury capsule. And then there's this outer layer, which is this sort of aluminized nylon kind of thing. And these were actually made by, I believe, B.F. Goodrich. So the people who make your tires were making these things, if that tells you how comfortable they were. And they trap heat. They're quite efficient at it because they have to, they're called get-down suits. If there were loss of pressure in the spacecraft, it would pressurize him enough so that he could get home without suffocating. So in that environment, not only is the suit terribly warm, but they would wear it for hours before launch, wear it the whole time they're sitting on the pad, wear it while they're in space, and then as they re-enter and while they're waiting to be picked up, in fact, they'd be wearing it all the way back to the aircraft carrier. So we see a lot more exposure of the suit time than we actually do the flights. And so here's some scatter plots of some of these data. The top one being body mass reduction and flight time along the bottom here, and it's actually suit time along the bottom. I take that back. And so these are the missions. MR refers to Mercury Redstone, MA Mercury Atlas, and that has to do with which rocket they rode on. So the MRs were the two suborbitals, the MAs were the orbital flights. And you can see this kind of logarithmic shape in all of it. And this is for hematocrits, which is the, see if I get this right, the percentage of your blood that is red blood cells, and or is it plasma? It's probably plasma. And then hemoglobin is just literally the amount of red blood cells essentially in your blood, measured as mass. Here's the correlation matrix between these things. So if we take a log of the suit time, it correlates quite highly to all of these things, which makes sense given that we expect this sort of thermal stress due to the suit. So what we did here is drew this very simple causal diagram where the suited time leads to some sort of fluid deficit or water loss, if you will, which is going to be reflected by body mass reduction, then also blood plasma volume reduction. So the body, once it starts to sweat out a bunch of water, will actually reduce the amount of water in your blood, and that will show up as increased hematocrit and hemoglobin. So then we put some letters on here to represent the pass, and by decomposing the correlation matrix here, we can actually solve for those standardized partial regression coefficients across the whole diagram, even though there's two latent variables right there in the middle. Then to understand the direct effect of, or the total effect of suited time on, say, hemoglobin, you just have to multiply ACE, which is what these rows down here do. And so that tells us for each standard deviation above the mean in the log of suited time, you would expect to increase the hemoglobin by 0.84 standard deviations above its mean. So kind of a nice, tidy way to understand this whole system of variables without having to actually measure everything involved. Next is astronaut smoking and mortality. So one day I was thinking about the fact that watching some historical reels, you could see astronauts smoking pre-flight, post-flight in the control room. And it turns out that in 2001, the LSAH put out some data on this that I was able to find. And so this little plot is from the Longitudinal Study of Astronaut Health newsletter put out in November of 2001. And it shows us the comparison trend line is the United States general population. Oh no, that's, sorry. Let me reframe this whole thing. Let me go back to the start here. You got the astronauts in red, the comparisons, the blue diamonds. So the LSAH in the beginning selected civil servants from Johnson Space Center to serve as controls for incidence calculations on any sort of disease that they were looking at. So that's the blue scatter plot. The blue line thus corresponds to that. The red line corresponds to the astronaut trend, and the green line is the general population via the National Health Interview Survey. So you can see, interestingly, that the astronaut trend pretty much mirrors the general population, but for some reason, the engineer and management type people at Johnson declined much quicker in their smoking rates over time. Nevertheless, there's the information. I was able to harvest this out of the plot here and combine it with my database of astronaut information so that I could make this nice table where we see the selection classes represented in the plot, how many people were picked, the person years that they've contributed up to when I did this, which was a couple of years ago, mean age at selection, the number of smokers that were in that class, because that was some of the data published along with this plot. And then I knew how many people had died from either cancer or CVD, and that allows us to calculate some crude rates. The question becomes, was that smoking detrimental to the astronauts? Did the classes with more smokers have higher mortality rates from either of these causes? The problem I had, as usual, was not knowing, though I knew how many smokers were in there because of these prevalence numbers here and the class size. Didn't know who the smokers were, so it was hard to know if the smokers were the ones who died. So I thought, okay, can we estimate this without knowing that? First approach is a simple relative risk analysis, where if we know how many people are in the class and we know the prevalence, we can get the number who were smokers and we know the number who died. And if you know relative risk, it's the probability of dying having been a smoker divided by the probability of dying having not been a smoker. So A over A plus B divided by C over C plus D. And what you can do then is essentially, this is for, I think this is just for Mercury. This is the first 7 astronaut class. You can do all the combinations by just saying, okay, how many of the dead people were smokers? Was it 0 or was it all of them? And you can do everything in between. And so you can see if you look at the number of dead among the smokers, or smokers among the dead rather, if you say, okay, among the Mercury guys, and I think I took it out 10 years post-selection so that there would not be confounded by observation time in order to make this table work, you can see that you don't really start getting a problem until 3 out of 4 smokers were the ones who died, or 3 out of 4 of the dead were the smokers. If it's only 1 or 2 of the dead smokers, then it doesn't increase the risk because those confidence intervals overlap the 1.0. But once you get out to 3 or more, that's when you start to see elevated risk. Another approach was a kind of bootstrap type of thing. So what I did here is just fit a model for the smoking, randomly assign smoking status to the astronauts, do a Poisson model, calculate an MRR, which is a mortality rate ratio, and then do it like 10,000 times and see where it's centered. And so you can see it's only a little bit above 0. The average was like 1.02. That's the median there, very close to 0. And then perhaps the most obvious choice, which is just do a group level model where you use the outcome as aggregate deaths from cause. The exposure is just the prevalence in that class, and use an offset of the person years they all accrued. Turns out mean age at selection wasn't really meaningful, but as you can see from the table, it was definitely confounded by selection year. And again, we see a very small effect that's not really significant from conventional 0.5 standards. Okay, only a couple more to go because I do want to give anybody a chance to ask questions. International astronaut mortality, the gist of this one is simply that if you look at Canada, Japan, Europeans, and Chinese, they have astronauts too, but no one's died. So how do you do a mortality analysis? What we did is essentially say, okay, what if everybody keeps living? At what point does the lack of death become significant? And that's what these plots show you here, is that ESA's already hit it, in that they've had enough astronauts who've lived long enough that the lack of death is becoming conspicuous. This quote over here says that basically because of the low background rates in Japan, you'd have to have all of their astronauts survive to 2035 before you'd see a similar conspicuous lack of death. And then here, suitability of comparison groups. Everybody's always saying, why don't you use the non-flight astronauts as your comparison for the flight astronauts? Doing it basically 6 different ways of trying to calculate propensity scores and either weight or model through matching, we found that really there's no method that can get you an unbiased comparison group, even though this one comes kind of close. It's just the reality is there's not enough non-flight astronauts because the people who haven't flight are the ones who are still on roster waiting. So long-term follow-up's not really useful. And then our helpful chart to help you determine risk of whether or not you're at risk of bear attack. So if you're in this zone, you're okay. And if you're over there, you're okay. And really very high risk here on Earth. So if you'd like to connect with me, I always welcome that. There's my email addresses, and you can connect with me on LinkedIn. And for what little bit of time, I think we have about 10 minutes. So I'm happy to entertain any questions or comments in the time that remains.
Thank you, Robert, very much for very clear, very nice talk. it is visible that you have also epidemiology background, because some of these models at the end are sort of quite popular there.
Yes, those are the bread and butter type of approaches in our discipline.
Yes. So I'm opening question and answer part of the talk. We check if there is a question the chat. No. So you can just raise your hand or just go ahead and ask question, Robert. So let me maybe start with question about DAGs, directed acyclic graphs, Bayesian ones. The key thing there is to elicit the probabilities. How
Yes.
NASA goes about the elicitation? Do you have consultants who are experts in assessing those?
Well, that's something we're thinking about now. We spent the better part of the last 4 years organizing hundreds of scientists to draw 30 diagrams, and then we had to troubleshoot them and make sure they all fit together like so many puzzle pieces. And now we're thinking about, where do we get those probabilities? So we're sitting on a lot of evidence. We're sitting on analog evidence from animals and nematodes and fruit flies and everything you can think of. We're sitting on limited spaceflight evidence. And then we have a lot of ground simulation analog type data that looks at very specific things. For example, there's a fake spacecraft and a fake Mars habitat here at Johnson, and they do a lot of teams and psychology type testing in there. They use Antarctic ground stations to look at immune dysregulation, bed rest to look at fluid shifts and bone loss. So the question becomes, how do we use all the data we have and or what's available in the literature to try to characterize all the probabilities that we need? It's an enormous effort, and I don't know that we'll ever actually finish it. But the question becomes, can we isolate the pathways where it's most important? And I think that's what some of the D-separation and path tracing type algorithms can do for us, is help us narrow that field down. So if anybody has any great ideas or wants to help, talk to me after.
Yes. Any other question for Robert?
Either I've done such an excellent job that everyone understands everything perfectly, or we're all on vacation brain here and it's time to just wrap it up.
I don't know that I really have a question, but I just wanted to say it was a very interesting talk, because some that I personally have never come across. So nicely done. Thank you.
I'm sorry, could you say that again? You've personally come across?
I have not personally come across this, so it was very interesting to see this application.
Well, thank you. Yeah, I'm one of the zany ones. I think if you were to get a more mainstream presentation out of the biomedical research labs, you'd see a much more polished academic style grant seeking and paper writing type of operation. I tend to exist on the fringe, trying to think about creative ways to bring more out of the data. So I'm glad you enjoyed it, though.
Any other comments, questions?
So one thing I would point out, and I'll go back in the presentation here. Let's see. The 3 documents I referenced are publicly available, these things, and that's what these URLs are. So if you really want to see all of the 30 causal diagrams and you want to understand this system as we've implemented it, you can download these things and take a look. And if you want to get involved in this sort of research, this is an excellent guide, because this shows you the state-of-the-art thinking that our experts within NASA have about how these risks work. Because every time one of these pictures was drawn, it wasn't just the 4 or 5 people in the risk custodial team. It actually got socialized at the HSRB, and the entire directorate had an opportunity to comment on these things. So they've been crowdsourced within NASA, and we would love to have them crowdsourced outside of NASA by having more scientists see these things and tell us where we got it wrong, or tell us where we can at least make it better. And if you wanted to try to do some space-related research, this is a way to make sure your grants that you put in are relevant and directed at the things that the agency cares about, which would, of course, increase their chance of getting funded, theoretically.
Yes. Thanks very much, Robert. As regards the current statistical research, I guess that causal learning and causal inference is very hot topic in the last few years. So that is something that should be attractive to graduate students.
Yeah, I would think so. And we're trying to plow some new ground here by bringing in some of those analytic approaches that are typically not associated with the causal diagram. So the social network analysis and the SEM, structural equation modeling type approach, typically all those domains were in silos too. People thought about social network analysis for sociology, and they thought about SEM for psychology, and they did DAGs and sort of the Bayesian networks and deseparation in computer science, and nobody was really talking to each other. But if you've got a basic network structure, there's no reason you can't do all of these things and really see what it tells you.
Yes. Any other questions? If not, let me thank you, Robert, and thank you all for attending. And stay in touch with Alma Mater.
Yes,
and
I'll
be
do my
going to
best.
stay in touch with you.
Gig 'em.
Thank you.